Hey everyone, so today we're going to be doing a video walkthrough of discussion 8. So discussion 8 is on asymptotic analysis. One thing I'm going to write real quick before we dive in is these two sums that will come in handy. Actually, I'll write it in a different form. So these two sums are basically every single asymptotic problem, or what they all boil down to. So it's very important that you either memorize these or put them on your cheat sheet. So the first one is an arithmetic sum. It's going to be this, 3 plus 4 plus, and it goes on until it hits the last number, which we're just going to call n. Note that in this case, it's increasing by 1, but as long as it increases by some constant number, then it's going to be we're going to have the same result. And that result is, we're going to say that this sum, the value of this sum is about n squared. You can use the arithmetic sum formula if you want to actually find the exact quantity it equals, but for runtime, that doesn't matter. Okay, and remember, it could have also been like 1 plus, I don't know, let's say we incremented by 2, right? So then it would be 3, 5, 7, n. And that would still be theta of n squared. It doesn't matter how much you increment by, as long as it's constant. That's what really matters. Okay, so that's the arithmetic sum. Now let's look at the other sum. It's the geometric sum. It's going to be 1 plus 2 plus 4 plus 8 plus ... n. And that's going to be theta of n. And the reason that this one is n and not n squared has to do entirely with the fact that this is a geometric sum. So geometric sums, they grow so quickly that the entire sum is basically captured by the last number in the sequence. Specifically with powers of 2, the sum equals, I think, n minus 1 or n plus 1, something like that. It's 1 different than the last term. Or I guess it would be 2 times, yeah, it's actually ends up being like 2n plus 1 or something like that. But the key idea is that the last term basically captures the entire sum for geometric ones. And again, we didn't have to multiply by 2. We could have multiplied by 3 or 4 or whatever, as long as it's some constant. Okay, so now we got those sums out of the way. Let's go to the first problem. Okay, so the first problem, we're doing runtime analysis. And specifically, we're doing best versus worst case. So best and worst case runtime analysis. And you might be a little thrown off by this problem because it has 2 inputs, m and n. Well, the good thing is that doesn't really complicate much. Actually, doesn't really complicate anything. So the only difference is now we just have 2 variables. It's not really, you still do the same process and all. And now we're just going to treat m as a variable too. So our bound might have m as well as n. Okay, so let's go ahead and start with the best case runtime analysis. So when you're doing best versus worst case runtime analysis, you should look at what opportunities there are for the function to run slower or faster. Let me show you what I mean by this. If you look at lines 2 through 4, there's not really much room for anything better or worse to happen. Right? It's no matter what n or m is, it's always going to do those same things because we need to assume properties of n and m that would allow this function to do better or worse. And that almost always has to do with if cases or maybe even a while loop, as long as there's some sort of condition that will allow the function to go faster or slower. And the one if statement we see here is the one on line 5. And it says, from the instructions, that slam is a constant time Boolean function. And so if slam happens to be true, we get to take this shortcut break statement right here. In the best case, so maybe I should clarify. First, we're going to start with the best case, and then we'll do worst case. In the best case, we always want to take this break statement. It's sort of like a shortcut out of this loop on line 4. So we know that in the best case, we want to somehow always take this break statement. So let's start off with that. Okay, so we know we're going to take this break statement every single time. Okay, so if that's true, then this loop from line 4 to line 7, the loop with j in it, it's only going to run once for every iteration of loop on line 3, right? Because this whole loop, we know that it's going to break on the first iteration if somehow slam of I and j is always true. And so for the best case analysis, we can assume that. That's something we're going to assume, that the input is such that slam I and j is always true, so we always get to take the break statement. Okay, if it's always true, we know that this whole loop is going to run in theta of 1 time, because it only iterates once. It's never going to go more than once. Okay, so now all this function is doing is this loop on line 3, where the body of the loop is constant time. So we know that from line 3 to line 8, that loop, that's just going to be theta of n. And that's because we're incrementing by 1, starting at 0 until we get to n. Okay, so we know the top part is theta n. What about the bottom part? Well, the bottom part, we're starting at k equals 0, and k is less than 1,000 n, and k is increasing by 1. So maybe you're tempted to write, okay, in the best case, it's theta of the n we got from the top plus 1,000 n that we got on the bottom. And that would be incorrect because that's not actually simplest form. Because remember, in theta bounds, we don't care about any coefficients. Okay, so what would that coefficient be? It would be the n we got from the top plus the 1,000 n from the bottom. And we know that that is theta of just n, right? And so that's what we write here, theta of n. Okay, cool. So that's best case for this function. Now let's analyze the worst case. Okay, so this is no longer going to be theta of 1. Let's remove this for now. Okay, so in the worst case, we kind of have the same idea. It's definitely going to be with this if statement on line 5. But now instead of that if statement always being true, we're going to have it never be true. Because in the worst case, we want to make this function go take as long as possible. If we want to make it as long as possible, we shouldn't take any shortcuts, so no break statement. Okay, so in the worst case, we're going to assume. In the worst case, we're going to assume that this if statement is not even there, that we're not even going to be able to take that break statement. Okay, so then how long does this, the body of the loop, so line 4 through 7, how long does that take now? It's going to be theta of what? Well, we know that from line 2, j starts off as 0. That's why there's like an empty semicolon, empty like initialization over there. So the first time on when I equals 0, the first iteration of I, this will run m times, right? Because we're starting from j equals 0, we're going to increment j by 1, and we're not going to stop until j is greater than or equal to m. So that's going to run m times, but only for the first iteration of I. The next time, we're not going to reset j to 0 because that is done on line 2. So actually, only for the first iteration, when I equals 0, will this loop do anything. The loop on lines 4 through 7. So only on the first iteration is this loop going to do anything, right? Okay, so, not this loop. This loop. This loop. So on the first iteration, this is going to be theta of m. But every iteration after that, it's going to be theta of 1. Because j is going to be 0 always for those not 0. J is going to be m always for those subsequent iterations. Because j is not reset. Okay, so in the worst case, it's going to be theta of, well, this loop is now going to take n time, definitely, but then also plus m time for that very first iteration of I, where we know that this does m work. Okay, and this part here that's still theta of n time, like we talked about earlier. So that's kind of noted in this term here. So you shouldn't write something like 1001 n plus m. It's just theta of n plus m. So going back to what we were talking about earlier, just because it's in two variables, that doesn't really complicate too much. We're just treating them both as variables now, and not as constants. So now we have m in our bound as well. And so let's talk about why we did not say that this function was omega of n and O of n plus m. So when it's talking about the best and worst case runtimes, it's kind of limiting the possible inputs. So in the best case, like we said, the inputs were such that slam of I and j is always true. And in the worst case, slam of I and j was never true. And so the reason we don't put a theta there is because in the best case, we're not even looking at the inputs where slam of I and j is not true. We're not even going to consider those inputs. So for the best case, every single input to our function will take that break statement every single time. So it's theta of n, not omega of n, not O of n, but theta. And the same kind of reasoning is for the worst case. We're only looking at the inputs where slam of I and j is never true. Okay, so that's why these are tight bounds, not like lower bounds or upper bounds. Okay, I'll skip the extra for now, and maybe if we have time, we can afterwards talk about it. Okay, let's look at a recursive function. Okay, so with recursive functions, you should basically always write out what's called the recursive tree. I'll show you what that means in a second, and also note we're doing best and worst case here. But if we look at this function, just like how earlier we talked about looking for opportunities for the function to go faster or slower, we actually do not see that here. So there's nowhere in here where there's opportunity for the function to be slower or faster based on a property of n. Maybe you think, oh, there's an if statement right here. What if I pass in a negative n? And to that, well, asymptotic runtime is only defined for very large positive n inputs. So that's not something we're going to be considering at all for this function and for the other functions in this course. Okay, so from that, we can deduce that the best case must equal the worst case, meaning there's no distinction between cases here. Okay, so now that we know that there's not really a distinction between best or worst case, now we can start drawing out the recursive tree. Okay, so this is how I like to draw out my trees. So first, we're going to start with the root. So the root, it's going to be just n. And you should think of the root as kind of corresponding to this, whatever the inputs are. In this case, we just have one. And in most cases, it will just be one input for these recursive, or at least one variable. Okay, and now, since we're going to be drawing a tree, the two important things are, the one is the branching factor. I'll say branches. And the two I'll call is the reduce in problem size. What that means is this thing I've written inside this node, this n, that corresponds to how big the problem is. Or you can think of how big the parameter is, or variable. And so what this means is if somebody gives us a, like this, someone calls and slam on some number n, so they've given us this, right? They've given us this problem, and now we need to compute that. And because it's recursive, right? Because it's recursive here, we can draw a node here to another problem. And why did I write n over 2 here? Well, that's because in the recursive call, we call it on n over 2. So note that at least for right now, I've completely ignored this part. We'll come back to that. That's actually part 3 that we need to know. Okay, so now I know that if someone gives me a problem of size n, what I'll first do is a little bit of work over here, and that, again, we'll calculate later. And after I do that little bit of work, I'll then do a recursive call on a smaller version of the problem. So this reduce in problem size, so like for number 2, for example, here, that is like the way you figure out what the reduce and problem size is you just look at the parameters of the recursive calls. And how do you figure out the number of branches? It's just the number of recursive calls. In this case, there's just one, so every node will have one branch. If every node has one branch, it's basically like a list, right? Because if I go to this problem, what's the reduce and problem size? Well, it's going to be n over 2. In this case, n is equal to n over 2, so it's going to be n over 4. I'm going to start going sideways now. And this is going to keep going. We're going to keep dividing by 2 until what? That's when we should check our base case. Until n is greater than 0. Okay, so the last node we can just write is equal to 0. You could have written 1 or maybe even -1 if you wanted to. That doesn't really make a difference as long as it's like pretty close to what the actual base case is. Because we're doing asymptotic runtime, the small differences can be kind of cut off. So for example, even if this was n is greater than 10, we could still put 0 there for our analysis. Okay, so we're almost done. Now we need to consider number 3. And the number 3 is going to be work per call. What work per call means is this stuff I alluded to earlier. So the way recursive functions always work is first the recursive the function will do some work. In this case, it's this double for loop. And then it's going to recursively call itself a few times. In this case, just one. And so if we want to find out how much total work is done, we need to figure out basically the sum of all the work done in each recursive call. So we know that this recursive call does how much work? Well, we need to analyze the double for loop. So it goes from I equals 0, incrementing by 1 until we hit n. And then what's this? We don't see n in here at all, which means it's constant, right? Because nothing in here is dependent on n, or I for that matter. So it's all with j's and this constant 1024. So this whole thing in the middle, that's just some constant runtime. So we can completely ignore that. And so this double for loop is basically just a single for loop that has runtime theta of n. So I'm not going to write theta here. I'm just going to write the actual number. And so this kind of corresponds to, or this does correspond to, how much work this and slam of n does, but only at this call, not the subsequent calls. So we need to do what we did here to all the recursive calls. Okay, well, how much work, if instead of passing an n, I pass n over 2, what does the work become now? Now it's not going to be n, but it's going to be n over 2. Okay, and what about, we'll write it over here. What about this call here? It's going to do n over 4. And what do we do with all these? We're going to add all of them. So let me move actually down over here. So let's rewrite that tree. So n over 2, n over 4, and we're going to keep going until 0. Okay, we noted that this does n work, this does n over 2 work, this does n over 4 work, and we will keep going, and this bottom one will do 0. And what do we do to all these? We're going to add all of them, because each one of these nodes represents one call to the function. And so if we want to find out how much work the function does in total, we need to add all of these up. So now we have this sum, n plus n over 2 plus n over 4 plus ... 0. So this may look like an unfamiliar sum, but it's actually one that you already know. I'm going to write the sum backwards. Okay, 0 plus, and now you may be considering why I put 0, because we know, okay, if you want to go from here to the next term, you divide by 2. But if you want to go to the previous term, you multiply by 2. So maybe you're thinking, okay, so the next term is 0 times 2, which is 0. So maybe you think I put 0 here. But the reason it actually ends in 0 is because Java will when you divide by 2, or when you divide, it's integer division. So really, this probably came from a 1, or it did come from a 1. So it doesn't really make much sense in math, but when you think about how Java does division, that's how we get our 1. Okay, then we'll get a 2, then a 4, and we'll keep going until we hit this term, right? This n. And we know from earlier that this is just a geometric sum. So this is theta of, what's the last term? Just n. And that's it for that one. So let's go write that in. Yeah, I'll delete that. Whoops. Okay, so we noted that this is just theta of n. And remember, the best case and the worst case, there was no distinction between them, so that's our answer in all cases. Okay, now let's go to this one. So here we have a bunch of inputs. We have someone's passing in an array, this low, and this high. So maybe you think, oh, I have 3 different inputs to my function, so my runtime might have 3 different variables. Well, actually, the array has, we're only figuring out the runtime for this specific call. So for some array that has length n, where low is 0 and high is n. So here it kind of, it definitely is useful to do some analysis of the function before you start writing down the recursive tree. And so let's figure out what this function is doing. So, okay, let's look at this. What is this thing? It looks like this is just kind of doing some, not constant work because it depends on low and high. So this is just some, we'll just write, this is just some work per call, right? Every call of this function is going to do this much work. And then it prints something, we can ignore that. I'm talking about the line 6 print, we can ignore that. And then what this is here, if you looking ahead to these to these 3 recursive calls, this is just basically a base case. If high minus low is not less than is not greater than 1, then we've kind of come to the end of our function or end of our work, and that's because high and low start off as n and 0 respectively, and each call to the function each recursive call, lines 10 and 12 and 13, bring low and high even closer together. And eventually they'll either meet or cross or be 1 apart. And once that happens, we're just going to say we're done. So that was just the analysis of the function beforehand. So let's note that this is basically just a base case. Okay, and now we can do best and worst case analysis. This is important. So this problem is not asking us to find the best or the worst case. It's just asking for the runtime. But if you look over here, there's like 2 possibilities. We either make 2 recursive calls in the case where coin is less than or equal to 0.5, or we only make 1 recursive call. And that's going to drastically affect the runtime of the function. So we can't quite say that the function, we can't quite just follow one of these. Like we can't assume, okay, coin's always more than half, and then just do analysis where it always does line 10. And we can't do the opposite. We can't assume it always does lines 12 and 13. So here what we're going to do is we're going to use best case and worst case analysis to describe the function. So this is how I like to think about it. You have this number line of runtimes. So maybe over here you have theta 1, maybe you have theta log of n, theta of n, and let's throw theta of n squared in there. So you kind of, and this number line goes on, right? I guess it wouldn't really go on in this direction, but it would definitely go on in this direction, right? It'd go to like n cubed and n to the 4th and all sorts of weird things like e to the n. Okay, and so what we can say is our function is going to be in some kind of interval. So we're going to say our function, it's not going to be this interval I'm writing, but maybe you figure out bounds on your function. So you say, okay, it's not always going to run in a specific runtime, but it's definitely going to be in this range. So maybe, for example, log n to n, right? And what that means is you can say your function is omega of, in this case, log n, and O of, in this example, n. So that's what we're going to do to bound the function. We're going to figure out what this omega should be and what this O should be. And that's computed using best case and worst case analysis. So let's delete this stuff and figure out what our bounds should be. So we're going to first go ahead and start with the best case. And in the best case, if you think about best case as the function is, oh, whoops, this didn't get deleted. If you think about best case as the function doing less work, you're going to want to take line 10, right? Because line 10 is definitely less work than line 12 and 13. So we're going to assume for best case that it always does line 10. Okay, so now let's figure out what the tree looks like. I'm going to go ahead and write it on this page. Okay, so someone's definitely going to pass us a problem of size n. Okay, and now, or actually we don't know how many branches there are yet. Let me rewrite what we want to know. So we want to know 1, the number of branches. 2, the reduce in problem size. And then 3, we want to know the work per call. Okay, let's go back. I guess we don't really need this. Okay, so these are the 3 things we want to find out. Let's go here and let's figure them out. So again, we're doing best case, so we're always going to take line 10. So there's only one recursive call. Okay, so we figured that out. That's just 1. Okay, so this is just, in our case, oops, this is just 1. The reduce in problem size, let's go figure that out. Okay, and so okay, this part for this question is a little bit different than other ones. So we see the recursive call is now doing, so low will stay the same, but high changes to low plus this quantity high minus low divided by 2. And the array stays the same. And for this part, maybe you're kind of confused. What is the change? Like, what is the problem size even? And that's when we need to go back to this first part, the work per call. Okay, so this part here. And so we note that this this for loop right here, it goes from low to high and does constant work for every kind of number between those things. So what happens is if the difference between high and low was super big, like 1,000, that would make this run way slower than if the difference between high and low was small, like 10. Okay, so that's what we're going to define as our problem size. Problem size. And let's call it m. And it's going to be high minus low. And with that in mind, we know that this work per call, it's theta of m. I guess I'll drop the theta here. Okay, it's theta of m. Or it's m, right? Because it just goes from low to high. And now we can figure out the reduce in problem size, right? Because it's going, the low stays the same, and then the high changes to the average of low and high. This, if you do the math, you can figure out this is basically low plus high over 2. And so that means the decrease in problem size is, so for example, if this was low, this is high. High is going to change to be in the midpoint, right? High is going to change to be the average of them. So m is going to become m times a half, and then it's going to be m times a fourth, and so on, right? So that's our decrease in problem size. It's just iteratively getting, or recursively getting divided by 2. So let's go back to here and write that down. The reduce in problem size, it becomes m over 2. And then the work per call, we noted, was m. Okay, now we're ready to draw our tree. So in the best case, it's going to be size m, one recursive call because there's one branch, m over 2, and m over 2 because that's the reduced in problem size, and then m over 4, and then I'll go horizontally now, dot, dot, dot. I put 0 last time. Let's just put 1 this time. It will make a difference. Okay, and now we need to, we forgot to fill in the work per call. So this one, as we know, it's still m. So this does m. This one will do m over 2 because its input is m over 2. This one does m over 4. This one does 1. And again, we kind of have the problem we just had, right? It's m plus m over 2 plus m over 4 plus dot, dot, dot to 1. And we know that from earlier, this is just theta of m, right? Okay, so now we need to figure out what was the initial value of m, where again, m was we defined as the difference between high and low. And that's where you go to the problem statement. They said this is the initial call, right? Array 0, n. So the initial value of m is n. So we can write our best case. This best case is like a box here. And it's omega. Because remember, we're kind of doing the number line thing, right? So we found the lower bound. It's definitely not going to run any faster than n time, right? Okay, now let's do the other call, or the other case, the worst case. And now we're just doing an extra recursive call every time. And it turns out that if you do the math on this one, it's going to be the same. It's going to be, it'll be the same problem, reduce in problem size as the one on line 10. So now our branching factor is just going to increase. Everything else will stay the same. Okay, so let's write that out. Let's write it out over here. Okay, or here. Okay, so our branching factor is 2. I'll just say branches equals 2. I'll say reduce in problem size. It's going to be a factor of 1/2, or I guess m over 2. And 3, the work per iteration, or work per call, that just stays the same. It's going to be m. Okay, let's do this. So now this is the worst case. So someone's going to give us a problem size m. And now we have 2 branches. This one's going to be m over 2. This one's also going to be m over 2. And then each one of these will have 2 branches. This one's m over 4. This one's m over 4. These are also m over 4. And oops, it keeps going, right? And at the bottom, because the base case was 1, we're going to have a bunch of 1s, right? Okay, so now we can figure out how much work this tree does. This one's a little bit trickier than what we did earlier because now there's multiple branches. So we can still apply the same thing. We're going to, in this case, because it turns out to be a little bit easier, we're going to add not every individual node, but we're going to add by row. So we're going to add this row, and then this row, and then this row, and eventually every row. Okay, well the first row, or I guess I'll call it the first level, it's just m, right? Because we know that the work per call is whatever the input size is. Okay, in this case we have 2 nodes, and they each do the same work, right? Because they have the same input. So I'm going to say 2 times. And now what's the work that, for example, this one does, right? Well, because again, we know that the work per call is just m, and this input is m over 2, so I'm going to write m over 2 here. And the 2's happen to cancel, and that's going to be m. It turned out to be the same as level 0, as we call it, the first level. Okay, let's do the same thing for the next level. There's 4 nodes. Each one of them does m over 4. Oh, and again, we see these 4's cancel. Okay, let's try to do the next row, right? So the next row is definitely going to have 8 things, right? And that's because the previous row had 4 things. Each one of those things will have 2 branches. So 8 things. And what's the problem size going to be? Well, this problem size on the level previously was m over 4. And since reducing it, the reducing problem size is by a half, this is going to become m over 8. And again, these cancel, and we get m. And this is going to happen for every row. You can write a little proof if you want, or you can just extend our pattern and say it's going to happen to every row. And now we can just figure out what this sum is going to be. So every row is going to do m. So m for at row 0 plus m for, I'll write m0 just to denote what row that is coming from. Or I guess I'll write it underneath it. Might be better. This is from 0, that's from 1, that's from 2, until the last row, right? The last row of all 1s. And let's say that comes from row h, where h is the height of this tree. Well, what is the height of this tree? It's a binary, right? It's a binary tree. There's 2 branches. And every time we go down a level, we divide by 2. So if we were to go, so we're just figuring out, okay, I know I have to go from n to m over 2, m over 4, and so on, until eventually I get to 1, right? Because that's the last row in here. Well, how many times do I need to divide by 2 to get from m to 1? And that's just the definition of the log of m. So that's how many times you need to divide by 2 to go from m to n. Okay, so there's log of m levels. Each one does m work. So that's our runtime. Let's plug that in here. Oops. And that's our upper bound. O of n, because again, the initial value of m is n, times log of n. Okay, cool. So now we know our function is somewhere on that number line. So if we were to draw that thing again, it goes more here, but here it'll be n, n. Here it'll be n log n. And our function is somewhere in this range. It's definitely not going to be on the right side, right? It's definitely not going to be slower than n log n, because that's our worst case. And it's definitely not going to be faster than n, because that's the best case. It will be somewhere in between there. We don't quite know where, so that's why we denote it with the bounds. Okay, now we can move on to this one. And it's a recursive function, so we're going to figure out those 3 things. Okay, so again, let's write down what those 3 things should be. So number 1 is the branching factor, where I'll just say branches. The 2 is the reduce in problem size. And 3 is the work per call. Okay, let's figure out, and you can figure these out in any order, right? Let's just start with 3. Okay, this function is only 6 lines, and a lot of those lines are just like Java things, right? That. Okay, so really we have 3 actual lines. One of them is the recursive call. Line 5 is the recursive call, so that doesn't count. Okay, and so we're left with lines 2 and 3. Well, 2 is a constant time Boolean check, right? And line 3 is also a constant time just returning something. So nothing in this function is dependent on, or no runtime is dependent on n per call, right? So there's no for loop, there's no other function we call. So this work for call is just theta of 1. It's just 1 unit of time. Okay, so that one is easy. Let's look at the reduction in problem size. And for that, we look at the parameters. Okay, the parameters are all n minus 1. So usually we see n like divided by 2, or maybe you'll see n divided by some other number. But here we see n minus a number. Okay. And we'll see later, like when we do the analysis, why that's really bad. Okay, so the reduction, so we already have 2 of them. We have the work per call and the reduction in problem size. And the branches, that's easy. We just count the number of recursive calls. 1, 2, 3. Okay, cool. So now with these three pieces of information, we can make our tree. So okay, so now we're ready to write our tree. We know that the root has value n, and then we'll have n minus 1, n minus 1 again, and n minus 1 here. And each one of these will have three things as well, and there'll be n minus 2. I'm not going to write all of them. And then those would have three more things, and so on, until we get to the base case, right? Which is a row of all ones. So 1, or maybe zeros, it doesn't really matter. Okay, so in this case, so earlier in the n log n problem, instead of counting the work per node, I counted the work per level. In this case, it actually makes sense to do the work per node. And why does it make sense here? Well, the work per call is constant, right? It's just theta of 1. So another way to figure out the total work that this tree does is to also ask the question, how many nodes are there in this tree? Because each node does one work, right? So that it contributes 1 to the total work. So instead of counting, because then it would end up, you'd end up doing something like, okay, this is 1, this is 3, because there's 3 nodes here. The next would be 9, because each one of those 3 things spawns 3 other things, and so on. So we can just figure out, okay, well, how many nodes are there in this tree? Well, because it's perfectly bushy, right, it is, the branching factor is satisfied on every level, we just need to know what's the height of this tree. And the total number of nodes is just going to be theta of 3 to the h, right? Because 3 because that's the branching factor. Okay, so what's the height of this tree? Well, it's however long it takes to go from n, the original problem statement, to the base case, 1. And how do we reduce our problem size? Well, from here, we know we go by 1. So we would need to go down n levels to get to the bottom. Or maybe n minus 1, but in this case, it ends up not really changing much. Okay, so we know that h equals n. So there's 3 to the n things here. And that's our runtime, theta of 3 to the n. And so you might think that instead of 3 to the n, we can write, for example, 2 to the n to maybe drop a lower order coefficient or something. But that's actually not true for exponentials, because exponential, the base matters a whole lot when you're figuring out if it's like a faster function or a slower function. So in this case, it actually does matter that this is a 3 and not a 2. Okay, so we can move on now to the next one, which is down here. Okay, so here we're kind of comparing different algorithms based on what the, where am I? Yeah, we're just comparing different algorithms based on some information we're given. And we just want to know which one is guaranteed to be faster. And here we're going to assume that n is very large. And afterwards, we'll look at that assumption. Why did we need to assume n was very large? Okay, let's look at part A. So someone says that algorithm 1 is theta of n, and algorithm 2 is theta of n squared. You should read that, kind of, I guess, translate that to English, saying that algorithm 1 in all cases runs in linear time, and algorithm 2 in all cases runs in quadratic time. Well, because that's in all cases, there's no possible way that algorithm 2, which is quadratic, can be better than algorithm 1. So here we're going to say, yep, that's true. That's true that it's guaranteed to be faster. Okay, and that's because it's tight bounds, right? Theta and theta. Okay, let's look at part B. So someone says that algorithm 1 is omega of n, and algorithm 2 is omega of n squared. So does that guarantee that algorithm 1 is faster than algorithm 2? Let's look at this number line. So earlier, or not number line, I guess like asymptotic runtime line. Okay, so n squared. So if someone says something is omega of something, for example, if like algorithm 1, that means this. Algorithm 1 lies either exactly on this or somewhere to the right. And algorithm 2 lies exactly on here or somewhere to the right. And so someone has told us this information, and now they're asking, okay, is algorithm 1 always faster than algorithm 2? Well, no, because algorithm 1 could extend to this area, right? And so could algorithm 2. And they could actually both be, theta of something over here. For example, maybe n cubed you might think of. So it could definitely be that both these algorithms are theta of n cubed runtime, and that would satisfy both of these requirements, that algorithm 1 is omega of n, and algorithm 2 is omega of n squared. And so in this case, the answer is no. It's not guaranteed that algorithm 1 is faster than algorithm 2. Okay, let's do the same thing for the next problem. And that's how you should kind of think of omega and O bounds. They're kind of bounding you on this asymptotic number line. Okay, so now we have algorithm 1 is O of n, and algorithm 2 is O of n squared. Okay, so we have kind of the same situation, except instead of an arrow to the right, we're going to have an arrow to the left, because O upper bounds. So algorithm 1 is either on this line or to the left. Algorithm 2 is on this line, or on this spot, or to the left. And again, they could, both potentially meet, like over here. Maybe it's like constant time, or a square root n. It doesn't matter, right? As long as it's something less than both n and n squared. So again, here, I'm going to say, no, it's not guaranteed that they're faster. They could be the same speed. Okay, let's do the same thing for the next problem. Now algorithm 1 is theta of n squared. So here, we're going to denote that by this. Algorithm 1 is exactly here. It's not to the left, it's not to the right, it's just right here. And then algorithm 2 is O of log n. So that means that, actually, one thing I misread was that it doesn't matter that A1 is less than A2, as long as one of them is definitely less. So that does not change our answer to the previous ones, but it will change it for part D, as we'll see. Okay, so I didn't write n log n here, but it happens, or log n. Log n is smaller than any polynomial, including the linear n. So log n is somewhere over here. So someone says algorithm 2 is O of log n, so that means O, so it goes left. So it's either on here or to the left. And now we have a case where A1 and A2 are not intersecting, right? There's no way A1 and A2 could have the same runtime. So we know for a fact that A2 is guaranteed to be faster than A1, right? Because there's no way you can, there's no way they can cross, right? Or they can meet into the same spot because one of them was theta. Okay, let's move on to the next one. Now we have that algorithm 1 is O of n log n. And for the same reason that log n is smaller than any polynomial, n log n is somewhere in here. Because it's definitely slower than n, but it's also faster than n squared, right? Because you can think of, so this is definitely, because of this, it's on the right side of n, and because of this, it's not bigger than n squared, right? Because log n is smaller than n. Okay, so it's somewhere in here. The distances don't matter as long as they're on the right side. Okay, so someone says algorithm 1 is either on this line or to the left, right? Because it's O. And someone also says algorithm 2 is either on this line or to the right because it's omega. Well, because O and omega include the, whatever term, it's kind of like a less than or equal to and a greater than or equal to. Because they include that term, we can't say whether algorithm 1 or algorithm 2 is faster. You might be tempted to say that algorithm 1 is faster because it might lie on this side, but we can't guarantee anything, right? It could be that algorithm 1 and algorithm 2 are both theta of n log n, in which case none of them is faster or slower than the other one. They're the same asymptotic speed. So x here as well. So the only two cases where we can guarantee them were part D and part A. Okay, now we can go on to why do we need to assume n was large? And that's because that has everything to do with asymptotics. So with asymptotics, let's draw like a number line or a graph, let's say x and y. So we say that n squared, right, is slower than n. Well, if I chose carefully constructed coefficients, my n squared might grow really slowly like this. Let's say it's, or I guess x squared in this case. Let's say that this is x squared times 10 to the negative 6, right? Some super small constant. And let's say this is a line, and this line is like 10 to the 6 times x. So some super high sloping line. So it looks here that, oh, this linear term is always greater than the quadratic term. But if you go really far along the x-axis, then the quadratic term will always pass the linear term. That's just an example for x versus x squared, but you can do that for anything: n cubed and n log n, n and log n, constant and n, anything. So for that reason, if we did not assume that n was large, then we get sort of degenerate results where you find that a linear function is faster than a quadratic, or sorry, and a linear function is slower than a quadratic function, which might be true for small inputs, but for large inputs, definitely not true. Okay, so that was pretty long, but that concludes the discussion walkthrough for discussion 8. Yeah, we'll see you in the next one.